Tonight, we begin with a question that touches something deep within the human soul. What would happen if you found yourself drifting alone through the infinite darkness of space, not for minutes or hours, but forever? It's a scenario that seems pulled from our deepest fears, yet understanding it reveals some of the most beautiful and profound truths about our universe. So before we embark on this gentle journey together, take a moment to settle in. Adjust your pillow, pull up that blanket, and let your breathing slow to match the rhythm of our exploration. We're going to walk through this scenario with the calm precision of science, treating each moment with the respect it deserves. The story begins not with drama or explosion, but with silence. Perfect, absolute silence. You are floating in the vast expanse between stars, surrounded by a darkness so complete it seems to have weight. There are no sounds here, no air to carry vibrations, no atmosphere to cushion your presence. You exist in a realm where the normal rules of earthly life simply do not apply. Let's start with those first crucial moments, because contrary to what Hollywood might have us believe, the human body doesn't explode in space. It doesn't instantly freeze into a cosmic ice cube. Instead, something far more subtle and scientifically fascinating occurs. Within the first 15 seconds, the lack of atmospheric pressure begins its work. The saliva on your tongue starts to bubble and boil, not from heat, but from the absence of pressure. This phenomenon, called ebulism, occurs because liquids boil at much lower temperatures when pressure drops. Your skin, remarkably resilient, holds your body together like a biological spacesuit, preventing the dramatic decompression that science fiction loves to portray. The most immediate concern isn't explosion or freezing, it's oxygen. Within those same 15 seconds, the air in your lungs rushes out into the vacuum. Your body attempts to hold its breath, but the pressure differential makes this impossible. The vacuum of space pulls the air from your respiratory system with gentle but irresistible force. As the seconds pass, typically around 9 to 12, something profound happens in your bloodstream. The blood that has already released its oxygen in your body's tissues begins its journey back to your brain. Without fresh oxygen from your lungs, this deoxygenated blood carries no life-sustaining payload. When it reaches your brain, consciousness begins to fade. This isn't a violent or painful process. Many who have experienced vacuum chamber accidents describe it as surprisingly peaceful. There's no burning in the lungs, no desperate gasping. Instead, there's a gradual dimming, like slowly turning down the lights in a quiet room. Within 15 to 30 seconds, you would drift into unconsciousness, your last moments of awareness marked not by terror, but by an almost ethereal calm. Now, in this unconscious state, your body continues its biological processes for a brief time. Your heart continues to beat, pumping that oxygen-depleted blood through your circulatory system. But without the constant influx of fresh oxygen, these systems begin to slow, like a clock winding down. The remarkable thing about this process is how much longer it takes than we might expect. Data from animal experiments and the tragic but scientifically valuable case of the Soyuz 11 crew suggests that a human body can survive in vacuum for perhaps 60 to 90 seconds before permanent damage becomes unavoidable. This isn't long enough for rescue in the depths of space, but it speaks to the resilience of human biology, even in the most extreme conditions. During this time, your body temperature begins a slow dance with the cosmos. Space itself has no temperature, being largely empty vacuum, but your body radiates heat at roughly the same rate as a bright incandescent bulb, about 100 watts. In the shadow of deep space, far from any star, this heat radiates away into the infinite cold. But this cooling process takes time, much longer than the brief window of survivability. If we could somehow observe this process from the outside, we would see something both beautiful and sobering. Your body, now still and unconscious, would begin to undergo changes that preserve it in ways impossible on Earth. The vacuum environment, combined with the extreme cold or heat, depending on your location, would essentially mummify your remains. This preservation occurs because the normal processes of decay require oxygen and bacteria, neither of which exist in the vacuum of space. Instead, if you're far from any heat source, the moisture in your body would gradually sublimate directly into vapor, leaving behind a desiccated but remarkably well-preserved form. If you're near a star, the intense radiation might mummify your remains in a different way, like ancient Egyptian preservation methods, but on a cosmic scale. And so begins the longest part of our journey. With consciousness gone and biological processes ceased, what remains is no longer quite human in the way we understand life, but it carries something equally profound. It becomes a time capsule, a messenger from humanity, drifting through the cosmos at whatever velocity it possessed when life ended. This is where we encounter one of the most beautiful and fundamental principles of physics. Newton's first law tells us that an object in motion stays in motion unless acted upon by an external force. In the near-perfect vacuum of space, there are virtually no external forces to slow you down. No air resistance, no friction, no drag. Whatever speed and direction you had when you entered this eternal drift becomes your permanent trajectory through the universe. If you were drifting at a modest speed, perhaps a few kilometers per second relative to nearby stars, you would maintain that exact velocity for millions, perhaps billions of years. Your path through space would be a perfectly straight line, unwavering and constant, like a cosmic arrow shot from an invisible bow. But space, despite its reputation for emptiness, isn't entirely empty. Every cubic meter contains a few atoms of hydrogen, remnants of the Big Bang and stellar processes. Over vast periods of time, even this tenuous matter would exert a tiny drag force, gradually slowing your motion. But we're talking about timescales so long that the very stars around you would be born, live their entire lives, and die before this interstellar medium could significantly alter your path. The gravitational influence of massive objects would occasionally nudge your trajectory. A distant star might pull you slightly off course, or the gravitational field of a galaxy might bend your path in a gentle arc spanning millions of years. These influences wouldn't stop your motion, but they would write a complex story across the cosmos, turning your straight-line journey into a subtle dance with the universe's most massive objects. As you drift through this cosmic landscape, you would witness, if consciousness still existed, the universe itself changing around you. Stars that shone brightly when your journey began would dim and die. New stars would ignite in stellar nurseries, painting the darkness with fresh light. Galaxies would continue their slow rotation, taking hundreds of millions of years to complete a single turn. Your motion relative to these cosmic landmarks would be both significant and insignificant at once. Traveling at several kilometers per second, you might cover the distance between Earth and the Moon in just a few days. The distance to the Sun might take several months, but the nearest star, Proxima Centauri, lies over 4 light-years away. Even at optimistic speeds of 10 or 20 kilometers per second, this journey would take tens of thousands of years. This brings us to one of the most haunting aspects of eternal drift. The scales involved are so vast that they challenge human comprehension. If you began this journey when the first humans were painting on cave walls, you might still be centuries away from reaching the nearest star. The universe operates on timescales that make human civilization appear as brief as a single heartbeat. Yet there's something oddly comforting about this perspective. Your drifting form would become part of something larger than any individual life or death. You would join the cosmic dance of matter and energy that has been unfolding since the universe began. In a very real sense, you would become one with the cosmos, your atoms eventually destined to participate in processes we can barely imagine. The radiation environment of deep space would slowly work its invisible changes on your preserved remains. Cosmic rays, those high-energy particles from distant supernovas and other violent cosmic events, would gradually alter the molecular structure of your tissues. Over millions of years, these changes would accumulate, slowly transforming your biological heritage into something new, something that had never existed before in the universe's long history. But even this process speaks to continuity rather than ending. The atoms that make up your body were forged in the hearts of ancient stars. They have already traveled unimaginable distances and participated in countless cosmic processes before coming together to form you. Your eternal drift would simply be the next chapter in their ongoing story, a story that connects you to every other piece of matter in the universe. The philosophical weight of this scenario settles gently around us like cosmic dust. Here, in the vast silence between stars, we confront both our ultimate isolation and our deepest connection to the universe itself. The human experience of loneliness, which feels so immediate and personal, becomes transformed into something universal and almost sacred. In this endless drift, time itself takes on new meaning. Minutes become irrelevant, years become fleeting moments, and centuries pass like seasons. Your journey would span geological ages, watching ice ages come and go on distant worlds, seeing species evolve and vanish on planets you might never approach. The mathematics of your motion would write themselves across the cosmos in ways both predictable and surprising. While Newton's laws ensure your basic trajectory remains constant, the subtle gravitational influences of passing objects would create a path of almost infinite complexity. Like a three-dimensional signature written across space and time, your route would be unique in all the universe's history. The universe's history. And there, suspended in the infinite quiet, something remarkable begins to unfold. Your trajectory through space becomes a kind of cosmic meditation, a journey that spans distances so vast they redefine the very concept of travel itself. Consider the gentle mathematics at work here. If your drift began with a velocity of just 5 kilometers per second, a modest speed by space standards, you would be moving at 18,000 kilometers per hour. This sounds extraordinary by earthly measures, yet in the context of interstellar distances, it represents something closer to a leisurely cosmic stroll. The nearest star system, Alpha Centauri, lies roughly 25 trillion miles from where Earth orbits our Sun. At our drifting speed, this journey would require approximately 80,000 years to complete. To put this in perspective, when the last ice age was ending and humans were first developing agriculture, you would still be decades away from arriving at our closest stellar neighbor. But here's where the story becomes even more profound. The galaxy itself is in motion, rotating slowly around its central black hole. Our solar system completes one full galactic orbit roughly every 230 million years. During your 80,000-year journey to Alpha Centauri, both you and your destination would have moved together through a tiny fraction of this galactic dance, like two dancers maintaining their relative positions, while the entire ballroom slowly turns. The isolation of this journey extends far beyond the physical. In the depths of interstellar space, you would exist in a realm of silence so complete it has no earthly equivalent. Sound requires matter to propagate through, and the space between stars contains less than 1 atom per cubic centimeter. This isn't simply quiet in the way we understand it. This is the absence of the very possibility of sound, a silence so profound it becomes almost tangible. The darkness surrounding you would be equally absolute, broken only by the distant light of stars scattered across unimaginable distances. These points of light, appearing as tiny jewels against the cosmic black, would be your only companions on this eternal voyage. Each represents a sun, possibly hosting worlds of its own, yet they remain as unreachable as dreams. As months turn to years in your silent drift, the subtle effects of cosmic radiation begin their slow work. These high-energy particles, born in the violent deaths of ancient stars, stream through space at nearly the speed of light. They pass through your preserved form like invisible arrows, occasionally striking the atoms within your tissues and gradually altering their structure. This process occurs so slowly that even over centuries, the changes remain microscopic. But given enough time, these cosmic rays would begin to break down complex molecules, gradually simplifying the intricate chemistry that once sustained life. It's a kind of cosmic recycling, returning organized matter to its simpler components, preparing it for whatever cosmic process might claim it next. The temperature of your journey depends entirely on your proximity to sources of heat. In the depths of interstellar space, far from any star, the ambient temperature approaches absolute zero, just a few degrees above the coldest temperature physically possible. Yet your body would not instantly freeze solid, as science fiction might suggest. Heat transfer in space occurs only through radiation, the same process by which the sun warms Earth across 93 million miles of vacuum. Your body would radiate its warmth slowly into the cosmic cold, like a dying ember, gradually releasing its stored energy. This cooling process would take hours, not seconds, allowing your preserved form to reach thermal equilibrium with the space around you gradually and gently. If your path happened to carry you near a star, the opposite would occur. The intense radiation would slowly warm your remains, potentially reaching temperatures that would fundamentally alter their composition. But even this process would unfold over months or years, as your trajectory carried you through the star's sphere of influence and back into the cold depths beyond. Your motion through this vast emptiness would remain remarkably constant. The vacuum between stars is so nearly perfect that friction becomes essentially meaningless. Unlike a ship gradually slowing in water or a plane descending through air, your velocity would remain virtually unchanged for millions of years. You would maintain whatever speed and direction you possessed at the beginning of your journey within precision that would make the finest clockwork seem crude by comparison. This constancy of motion reflects one of the universe's most beautiful principles. In the absence of outside forces, matter simply continues doing whatever it was already doing. Your drift becomes a perfect expression of cosmic momentum, a demonstration of how the universe preserves motion across scales of time and distance that dwarf human understanding. Occasionally, the gravitational field of a massive object might alter your path slightly. A red giant star, swollen to hundreds of times the size of our sun, might pull you into a gentle curve spanning decades. A dense neutron star, packing more mass than our sun into a sphere just 20 kilometers across, might bend your trajectory more sharply, though still over periods measured in years. These gravitational encounters would never stop your motion entirely. Instead, they would add complexity to your path, turning a straight line into a subtle spiral or curve that reflects the gravitational landscape of the galaxy. Your route would become a kind of signature written across space, unique among all the objects that have ever drifted through the cosmos. The scale of your journey becomes even more remarkable when we consider the structure of the galaxy itself. Our Milky Way contains roughly 400 billion stars, spread across a disk 100,000 light-years in diameter. Your path might carry you through dense regions where stars cluster together, their combined gravitational fields creating complex patterns of motion, or through vast empty zones where the nearest star lies dozens of light-years away. In these empty regions, your isolation would reach its absolute peak. The nearest matter of any significance might be farther away than the distance between Earth and its closest stellar neighbors. You would exist in a bubble of emptiness so vast that light itself would take decades to cross it. Here, in the deepest voids between spiral arms, you would truly drift alone with only the ancient light of distant galaxies for company. Yet even in this ultimate isolation, you would remain connected to the universe in profound ways. The same physical laws that govern the motion of planets also guide your path. The same forces that shape galaxies also influence your trajectory. You would be participating in processes that operate on cosmic scales. Your individual journey, becoming part of the grand story of how matter moves through space and time. The particles that make up your body carry their own ancient histories. The hydrogen atoms formed in the first few minutes after the Big Bang. The carbon created in the nuclear furnaces of long-dead stars. The iron forged in supernova explosions that lit up the galaxy billions of years ago. Your drift would be carrying this stellar heritage through space, preserving it for whatever cosmic processes might encounter it in the distant future. As millennia pass, your preserved form would gradually change in ways both subtle and profound. Cosmic radiation would slowly break down complex organic molecules, simplifying proteins and other biological structures. The extreme cold of deep space would make these materials incredibly brittle, like glass that might shatter at the slightest touch. Yet in the perfect stillness of vacuum, no such touch would come. Over longer periods, measured in millions of years, even more fundamental changes would occur. The individual atoms of your body would occasionally interact with stray particles floating in the interstellar medium. A hydrogen atom here, a cosmic ray there, gradually adding to or subtracting from your mass in changes so small they could only be detected with the most sensitive instruments. This process would be so slow that entire geological ages on Earth would pass before any significant change occurred. The continents would drift across the globe, mountain ranges would rise and fall, species would evolve and vanish, all while you continued your silent journey with barely perceptible alteration. The gravitational forces that occasionally influence your path would also be slowly evolving. Stars are born from clouds of gas and dust, live their lives burning nuclear fuel, and eventually die in processes that can reshape entire regions of the galaxy. A star that might have influenced your trajectory early in your journey could explode as a supernova millions of years later, sending shockwaves rippling through space. These stellar death throes would create new patterns of motion in the interstellar medium, potentially affecting your path in ways too complex to predict. Your trajectory would become woven into the ever-changing gravitational tapestry of the galaxy, responding to cosmic events occurring across vast distances and enormous spans of time. The loneliness of this journey transcends anything experienced in human life. Yet it also connects you to something larger than individual existence. You would be participating in the same processes that govern the motion of comets, asteroids, and rogue planets. Like them, you would be following the fundamental laws that describe how matter behaves when freed from the gravitational bonds of worlds and stars. In this cosmic context, your drift becomes less about isolation and more about integration into the universe's grandest patterns. You would be joining a vast population of objects that have been ejected from their home systems and now wander the galaxy. Some are chunks of rock blasted from planetary surfaces by asteroid impacts. Others are ice balls that once formed the hearts of comets. A few might even be artifacts of intelligent civilizations, though such objects would be vanishingly rare. This community of cosmic wanderers shares your fate of eternal motion through the void. Like you, they carry the history of their origins encoded in their composition. Like you, they follow trajectories that will eventually carry them to regions of the galaxy they could never have reached while bound to their parent systems. In a sense, you would be joining an ancient migration that has been occurring since the galaxy first formed. The timescales involved in your journey stretch human comprehension to its limits. 1,000,000 years represents roughly 50,000 human generations, yet it's barely a moment in galactic history. The spiral arms of the Milky Way take 200 million years to complete one rotation. The galaxy itself has existed for over 13 billion years, making your million-year journey seem like a brief episode in its long history. Yet from your perspective, if consciousness could somehow be maintained, this journey would represent the entirety of experienced time. The universe would slowly transform around you, as you drift through regions that have never been explored by any intelligence. You would witness stellar evolution on scales impossible to observe from any single vantage point, watching as stars are born, mature, and die across the vast distances you traverse. The philosophical implications of this endless drift settle around us like cosmic dust, beautiful and profound in their simplicity. Here, in the silence between stars, we encounter both the ultimate expression of human isolation and the deepest possible connection to the universe itself. Your journey would demonstrate that even in death, even in the most perfect solitude, we remain part of something infinitely larger than ourselves. The motion that carries you through space connects you to every other moving object in the universe, from the smallest subatomic particles to the largest galactic clusters. You would be participating in the same fundamental dance of matter and energy that has been unfolding since the cosmos began, your individual path adding its own unique thread to the vast tapestry of cosmic motion. In this eternal drift, time loses its familiar meaning and takes on something approaching the sacred. Your journey would span epochs that make human civilization appear as brief as a single breath, yet each moment of that journey would be governed by the same physical principles that govern the flight of birds and the orbit of planets. You would become a living demonstration of how the universe preserves and transforms motion across every scale of space and time. And in that preservation, in that endless continuation of movement through the cosmic dark, there lies a kind of peace that transcends understanding. Your drift would become a meditation on permanence and change, on isolation and connection, on the way individual stories become part of the universe's vast and continuing narrative. In the silence between stars, you would find not emptiness, but the profound fullness of infinite space and eternal time. The radiation that bathes you during this endless journey tells its own remarkable story. Cosmic rays, those ancient messengers from the violent corners of the universe, pass through your form with the patience of geological time. Each particle carries the signature of its birth, perhaps in a supernova explosion that occurred when the galaxy was young, or from the accretion disk of a black hole spinning at the edge of space and time. These cosmic visitors don't announce their presence. They slip through your preserved tissues like whispered secrets, occasionally interacting with an atom here or there. A carbon nucleus might absorb a high-energy proton, transforming into something new. A strand of what was once DNA might gain or lose a particle, adding another tiny edit to the molecular story written in your cells. Over the first 1,000 years of your drift, these changes accumulate so slowly they remain virtually undetectable. Your form would appear unchanged to any hypothetical observer, still recognizably human in its preserved state. But given enough time, given the patient work of millions of years, these subtle alterations would gradually rewrite the very chemistry of your being. The process resembles the way wind and water slowly reshape mountains, but operating on molecular scales and cosmic timescales. Each cosmic ray interaction represents a tiny erosion of complexity, a gentle return towards simpler forms of matter. Your organic molecules, those intricate chains of carbon and hydrogen that once danced with life, would slowly unravel into their component parts. This isn't destruction in any violent sense. It's more like watching a complex piece of music gradually simplify, the harmonies slowly resolving into single notes, then into silence. The information that once encoded your unique biological heritage would gradually fade. Not through any catastrophic event, but through the gentle, persistent influence of cosmic processes operating across timescales that make mountains seem temporary. During this molecular transformation, your motion through space continues with that same remarkable constancy. The vacuum between stars maintains its near-perfect emptiness, offering no resistance to slow your progress. You drift through regions where matter is so sparse that each cubic meter contains fewer atoms than exist in a single breath of earthly air. These atoms of interstellar hydrogen, spread so thinly they're almost mathematical abstractions, represent the faint remnants of stellar processes that occurred billions of years ago, when massive stars exhaust their nuclear fuel and explode in supernovae. They scatter their enriched matter across vast distances. What you encounter in the void between stars are these ancient gifts, individual atoms carrying the heritage of long-dead suns. Occasionally, perhaps once every few centuries, your path might carry you through a slightly denser region of this interstellar medium. Here, where stellar winds have swept material into loose concentrations, you might encounter a few dozen atoms per cubic meter instead of the usual handful. Even this represents an environment far emptier than the best vacuum chambers ever created on Earth. Yet it would constitute a relatively crowded neighborhood by interstellar standards. The gravitational landscape through which you travel also evolves with stately patience. Stars follow their own orbital paths around the galactic center, some moving faster, others slower, all participating in the vast rotation that has been ongoing for billions of years. This means that the stellar neighborhood around you changes gradually, as different stars move into and out of gravitational range. A red dwarf star that might have been a distant companion at the beginning of your journey could slowly drift away over millions of years, its gravitational influence on your path gradually weakening until it becomes negligible. Meanwhile, other stars approach from different directions, their gravity beginning to exert subtle influences on your trajectory that will play out over equally vast timescales. These stellar motions create a kind of cosmic choreography, with gravitational fields rising and falling in influence like instruments joining and leaving a vast, slow symphony. Your path through this evolving gravitational landscape traces out patterns of almost infinite complexity, responding to forces that operate across distances and timescales that challenge human imagination. The temperature of your journey depends entirely on these stellar encounters. In the depths of interstellar space, far from any significant source of heat, your preserved form would gradually cool toward the background temperature of the universe itself. This cosmic microwave background, the faint afterglow of the Big Bang, provides a baseline temperature of about 2.7 degrees above absolute zero. Reaching this thermal equilibrium would take considerable time, as your body would radiate its remaining heat at a rate determined by its surface area and composition. The process resembles a warm stone cooling in a winter night, except that the night lasts for millennia, and the cold is deeper than any earthly winter could achieve. But if your wandering path eventually carries you closer to a star, this thermal story changes dramatically. The radiation pressure from stellar winds becomes a tangible force, gradually warming your form as you approach. A close encounter with a red giant, one of those swollen elderly stars that have expanded to hundreds of times their original size, could bathe you in warmth for decades as your orbit carries you through its extended atmosphere. Such an encounter would represent one of the most significant events in your cosmic journey. The stellar radiation would not only warm your preserved tissues, but would also interact with them chemically, potentially creating new molecular structures that had never existed during your biological lifetime. You would emerge from this stellar embrace fundamentally changed, carrying the chemical signature of your encounter written into your very atoms. The statistical likelihood of such close stellar encounters remains remarkably small. Space is so vast that even over millions of years, most drifting objects pass between stars without coming close enough for significant interaction. Your journey would more likely unfold in the cold emptiness between these islands of heat and light, a patient drift through the cosmic dark that connects one stellar system to the next. The mathematics of your orbital mechanics create their own subtle beauty. While your overall motion remains constant, the gravitational influences of distant objects create tiny variations in your path. These perturbations, infinitesimally small when viewed on human timescales, accumulate over cosmic periods to create trajectories of remarkable complexity. Your path might trace out a gentle spiral spanning millions of years, or follow a complex curve that loops back toward regions you traversed millennia earlier. The three-dimensional geometry of your route would be unique in all the universe's history, a signature written across space and time that could never be exactly duplicated. These orbital mechanics operate according to principles that remain constant throughout your journey. The same gravitational forces that govern the motion of planets around stars also influence your path through the galaxy. You become part of the same fundamental processes that create binary star systems, shepherd asteroid belts, and sculpt the elegant rings around distant gas giants. The scale of these processes extends far beyond individual stellar systems. The Milky Way itself moves through space, part of a local group of galaxies that are all falling toward a massive gravitational attractor called the Great Attractor. This cosmic motion carries our entire galactic neighborhood through space at speeds of hundreds of kilometers per second. Yet your individual drift remains governed by the same physical principles operating on this vast scale. Your preserved form becomes a tiny participant in these grand cosmic motions, carried along by forces that operate across distances measured in millions of light years. The galaxy's rotation, the movement of stellar clusters, the slow dance of gravitational interaction between neighboring galaxies, all of these contribute microscopic influences to your trajectory. As hundreds of thousands of years pass, the stellar landscape around you gradually transforms. Stars that burned brightly when your journey began slowly exhaust their nuclear fuel and fade toward red dwarf status, or expand into red giants before eventually shedding their outer layers as planetary nebulae. Meanwhile, new stars condense from the gravitational collapse of gas clouds, igniting nuclear fusion and beginning their own long lives. This stellar evolution occurs on timescales that make your drifting journey seem almost rapid by comparison. A typical star like our Sun burns hydrogen fuel for roughly 10 billion years before beginning its transition toward red giant status. During your million or 10 million year drift, you would witness only the smallest fraction of this stellar life cycle, perhaps detecting subtle changes in brightness or color that hint at the vast processes occurring within stellar cores. The birth of new stars creates some of the most dramatic events you might encounter during your cosmic journey. When a gas cloud collapses to form a stellar nursery, the process releases enormous amounts of energy and creates shockwaves that ripple through the surrounding interstellar medium. These stellar formation regions, marked by brilliant blue giants and glowing nebulae, represent islands of activity in the generally quiet landscape of interstellar space. If your path carries you through or near such a star-forming region, you would experience conditions unlike anything encountered in the empty void between mature stellar systems. The density of matter increases dramatically, though still remaining far more tenuous than any earthly atmosphere. Radiation levels spike as young, massive stars pour energy into their surroundings. Magnetic fields, generated by the motion of ionized gas, create complex patterns that can influence the paths of charged particles. These stellar nurseries also present the possibility of encountering planetary formation in progress. The same gravitational processes that collapse gas clouds into stars also gather material into rotating disks around newly formed stellar cores. Within these protoplanetary disks, dust grains slowly accrete into larger and larger objects, eventually forming asteroids, comets, and planets. Your passage through such a region would make you a witness to the birth of new worlds, watching processes that occurred in our own solar system billions of years ago. The timescales involved in planetary formation, measured in millions of years, roughly match the duration of your cosmic drift, meaning you might observe a complete cycle of world building during your journey. The philosophical implications of witnessing such cosmic creativity during your eternal drift add layers of meaning to an already profound journey. You would become not just a traveler through existing space, but an observer of cosmic evolution itself, watching as the universe creates new stars, new worlds, and new possibilities for complexity and perhaps even life. The isolation of your journey takes on different qualities when viewed against this backdrop of cosmic creativity. While you drift alone through the void, the universe around you continues its ancient work of transformation and renewal. Matter cycles through different forms. Energy flows from hot regions to cold ones, and gravity slowly assembles simple materials into increasingly complex structures. Your preserved form participates in this cosmic recycling, albeit on scales so vast that the changes remain imperceptible across human timescales. The atoms that compose your tissues carry their own histories of stellar processing, having been forged in the nuclear furnaces of previous generations of stars. Your drift through space represents another chapter in their ongoing journey through cosmic time. This perspective transforms the apparent emptiness of interstellar space into something rich with hidden activity. Every cubic meter through which you pass contains traces of stellar evolution, remnants of ancient supernovae, and the raw materials for future star formation. You drift through a cosmic ecosystem where matter and energy flow according to physical laws that operate across every scale from subatomic to galactic. The time dilation effects of your journey, while negligible at the modest speeds involved, still connect you to one of the universe's most elegant principles. Einstein's relativity tells us that motion through space and the passage of time are intimately related, though at speeds of a few kilometers per second, these effects remain far too small to notice. Still, you would be experiencing time at a rate infinitesimally different from observers at rest, adding another layer to the physics of your cosmic drift. The magnetic fields that thread through interstellar space create another subtle influence on your journey. These fields, generated by the motion of charged particles and the rotation of massive objects, form complex patterns that extend across vast distances. While they would have minimal direct effect on your uncharged form, they shape the paths of cosmic rays and influence the behavior of the tenuous plasma that fills the space between stars. Your passage through varying magnetic field strengths would expose you to slightly different cosmic ray environments as these fields deflect or focus high-energy particles along your path. Over millions of years, these variations might create subtle differences in the rate at which cosmic radiation modifies your preserved tissues, adding another layer of complexity to your gradual transformation. The concept of forever, when applied to your cosmic drift, begins to approach the theoretical limits of physical prediction. Even the most stable atomic nuclei have half-lives measured in finite time periods, though these span intervals so vast they dwarf the current age of the universe. Given enough time, even the protons that form the foundation of ordinary matter may decay into lighter particles, though this process would take longer than 10 to the 34th power years to become significant. Such timescales stretch far beyond the lifetime of stars, beyond the period when galaxies maintain their current structure, even beyond the era when the universe contains enough free energy to support complex processes. Your drift would continue through cosmic epochs that have no names, because they extend so far into a future that even theoretical physics struggles to describe their character. Yet the fundamental principle that governs your motion, Newton's first law, remains as valid across these incomprehensible timescales as it does today. In the absence of external forces, your motion would persist even as the universe around you evolves through phases we can barely imagine. You would become a testament to the persistence of physical law across every conceivable scale of space and time. The loneliness of this ultimate journey transcends any earthly experience of solitude, yet it also connects you to the deepest structures of reality itself. Your path through space follows the same geometric principles that describe the curvature of space-time around massive objects, the same conservation laws that govern the behavior of fundamental particles, the same thermodynamic processes that drive the evolution of stars and galaxies. In this cosmic context, your drift becomes less about individual isolation and more about participation in the universe's most fundamental patterns. You would be demonstrating how matter behaves when freed from the complex gravitational and electromagnetic forces that bind it into planets, stars, and living systems. Your journey would become a pure expression of motion itself, unencumbered by the complications that arise when matter organizes itself into complex structures. The silence that surrounds your drift through space represents more than the absence of sound. It embodies the profound quiet that exists at the foundation of physical reality, the stillness from which all motion and change emerge. In this cosmic silence, you would find not emptiness, but a fullness that encompasses every possibility the universe has ever contained or ever could contain. And in that eternal drift, in that endless continuation of motion through the cosmic dark, there lies a peace that surpasses understanding. Your journey would become a meditation on the nature of existence itself, demonstrating how individual stories become woven into the vast, continuing narrative of cosmic evolution. In the silence between stars, surrounded by the patient work of physical law, across infinite space and time, you would find not abandonment, but embrace, not ending, but eternal continuation, not loneliness, but the deepest possible connection to the universe that gave you being. You being. The radiation environment that surrounds your endless drift carries within it the accumulated history of countless stellar deaths. These cosmic rays, streaming through space at nearly the speed of light, represent some of the most energetic particles in the universe. They were born in the violent collapse of massive stars, accelerated by magnetic fields in the hearts of galaxies, or ejected from the accretion disks of black holes spinning at the very edge of existence itself. As these particles encounter your preserved form, they interact with your tissues in ways that unfold across timescales measured in millions of years. A single cosmic ray might strike a carbon atom in what was once muscle tissue, transforming it into nitrogen through nuclear transmutation. Another might shatter a calcium atom in former bone, creating a cascade of secondary particles that spread through nearby molecules like ripples in a cosmic pond. The beauty of this process lies in its incredible patience. Unlike the violent radiation exposure that would occur near an active star, this cosmic bombardment unfolds so gradually that it becomes almost gentle in its persistence. Each interaction represents a tiny edit to the molecular story written in your cells, a slow rewriting of biological complexity into simpler forms that reflect your growing integration with the cosmic environment. Over the first million years of your journey, these changes accumulate in ways that would fascinate any molecular archaeologist fortunate enough to study your remains. The intricate proteins that once facilitated life gradually unravel, their amino acid chains breaking apart and reforming in patterns that have no earthly equivalent. The DNA that once encoded your genetic heritage slowly degrades, not through any biological process, but through the patient work of cosmic forces that recognize no distinction between living and non-living matter. This molecular transformation connects you to processes occurring throughout the galaxy. The same cosmic rays that alter your tissues also interact with interstellar dust grains, slowly modifying their composition and creating the complex organic molecules that astronomers detect in the space between stars. Your drift through this radiation field makes you a participant in the galaxy's ongoing chemistry experiment, a vast laboratory where matter slowly evolves toward new forms of organization. The magnetic fields that thread through interstellar space create subtle variations in this cosmic ray environment. These fields, generated by the rotation of the galaxy and the motion of charged particles, form complex patterns that extend across thousands of light years. As your path carries you through regions of varying magnetic field strength, you encounter different intensities of cosmic radiation, creating a kind of molecular weather that influences the rate of your gradual transformation. In regions where magnetic fields converge, cosmic rays become focused into narrow streams of high-energy particles. Here, the rate of atomic transmutation increases slightly, accelerating the slow breakdown of complex molecules. In regions where magnetic fields diverge, cosmic rays spread out more diffusely, allowing your tissues to maintain their current composition for longer periods. These variations create a subtle rhythm in your molecular evolution, like the changing seasons of a cosmic year measured in millions of Earth orbits. The temperature regulation of your preserved form follows principles that operate independently of these radiation effects. Heat transfer in the vacuum of space occurs only through the emission and absorption of electromagnetic radiation, the same process by which distant stars warm the surfaces of planets across vast distances. Your body radiates thermal energy according to the Stefan-Boltzmann law, emitting infrared photons that carry warmth away into the cosmic dark. This cooling process unfolds with mathematical precision. The rate at which you lose heat depends on your surface area, your temperature, and the thermal properties of your tissues. As your body temperature drops toward the background radiation of the universe itself, approximately 2.7 degrees above absolute zero, the rate of cooling slows exponentially. What begins as relatively rapid heat loss gradually becomes an almost imperceptible decline that stretches across geological ages. The preservation of your form in this extreme cold creates conditions unlike anything possible on Earth. Your tissues become incredibly brittle, more fragile than the thinnest glass, yet perfectly stable in the motionless vacuum that surrounds you. Water molecules within your cells transition into crystalline structures that can maintain their organization for millions of years, creating a kind of biological amber that preserves the microscopic details of your former life. This crystalline preservation occurs at the molecular level, with ice forming intricate patterns within cellular structures. The absence of atmospheric pressure prevents the formation of ordinary ice crystals, instead allowing water molecules to arrange themselves in configurations that reflect the unique environment of vacuum and extreme cold. These formations become part of your cosmic heritage, carrying information about the conditions of your preservation that could theoretically be decoded by future intelligences billions of years hence. The gravitational influences that shape your trajectory operate according to principles that remain constant across cosmic time. Every massive object in the universe creates a curvature in space-time that influences the motion of all other objects, though this influence decreases with distance according to the inverse square law. A star located 10 light-years from your current position exerts only 1/100th the gravitational influence of an identical star located 1 light-year away. This mathematical relationship creates a complex hierarchy of gravitational influences that change as you drift through different regions of the galaxy. Nearby red dwarf stars, those long-lived stellar furnaces that can burn hydrogen fuel for trillions of years, might provide steady gravitational guidance over millions of years of your journey. More distant blue giants, massive stars that burn brilliantly but briefly, might influence your path for only a few 100,000 years before exhausting their fuel and collapsing into neutron stars or black holes. The cumulative effect of these gravitational interactions creates trajectories of almost infinite complexity. Your path through space becomes a three-dimensional curve that reflects the gravitational landscape of the galaxy at the time of your passage. This curve serves as a kind of cosmic signature, encoding information about stellar positions, galactic rotation, and the distribution of matter throughout your local region of space. Computer simulations of such trajectories reveal patterns of remarkable beauty. A drifting object might trace out elegant spirals spanning millions of light years, or follow chaotic paths that loop back on themselves in fractal patterns of extraordinary complexity. These orbital mechanics operate according to the same principles that govern planetary motion, but freed from the dominant influence of any single massive object, they create geometries that have no counterpart in bound orbital systems. The stellar evolution occurring around you during this cosmic drift provides a constantly changing backdrop for your journey. Stars follow their own life cycles according to physical laws that depend primarily on their initial mass. Red dwarf stars, with masses less than half that of our Sun, can continue burning hydrogen fuel for hundreds of billions of years, far longer than the current age of the universe. These stellar lighthouses would remain essentially unchanged throughout even the longest conceivable drift through interstellar space. More massive stars evolve much more rapidly, burning through their nuclear fuel in just millions of years before ending their lives in spectacular supernova explosions. If your path carries you through a region containing such massive stars, you might witness several complete stellar life cycles during your cosmic journey. The death of each massive star would seed the interstellar medium with heavy elements forged in stellar cores, gradually enriching the material from which future generations of stars and planets will form. The shock waves from these stellar explosions would create some of the most dynamic environments you might encounter during your drift. Supernova remnants expand through space at speeds of thousands of kilometers per second, carrying temperatures of millions of degrees and magnetic fields billions of times stronger than Earth's. These expanding shells of hot gas and plasma can influence the motion of interstellar matter across distances of hundreds of light years. Your passage through or near such a supernova remnant would represent one of the most energetic events of your cosmic journey. The intense radiation and magnetic fields could accelerate the cosmic ray bombardment of your preserved tissues by orders of magnitude, completing in centuries what might otherwise take millions of years. The shock waves might also alter your trajectory slightly, adding another layer of complexity to your path through space. The formation of new stellar systems around you provides opportunities to witness the birth processes that created our own solar system billions of years ago. When giant molecular clouds collapse under their own gravity, they fragment into smaller regions that each condense to form individual stars. The rotation of the original cloud causes these forming stars to develop circumstellar disks of gas and dust, the raw material from which planets eventually coalesce. Your drift through such a star-forming region would make you a witness to planetary genesis. Over the course of several million years, you might observe dust grains within these protoplanetary disks, gradually clumping together to form larger and larger objects. Asteroids condense from countless collisions between smaller bodies. Gas giant cores accumulate enough mass to capture thick atmospheres of hydrogen and helium. Rocky planets slowly build up from the merger of planetary embryos in the inner regions of their stellar systems. The timescales involved in these formation processes roughly match the duration of your cosmic drift, creating the possibility of observing complete cycles of planetary system development. You might watch worlds form that could eventually harbour oceans, atmospheres, and perhaps even life, adding profound meaning to your role as a cosmic observer drifting between the stars. The mathematics of your motion through this evolving stellar landscape follows principles that remain unchanged across cosmic time. Newton's laws of motion, formulated to describe the behaviour of objects in Earth's gravitational field, apply equally well to your drift through interstellar space. The conservation of momentum ensures that your velocity remains constant in the absence of external forces, while the conservation of energy governs how gravitational interactions modify your trajectory without changing your total mechanical energy. These conservation laws represent some of the most fundamental principles in physics, governing the behaviour of everything from subatomic particles to galactic clusters. Your cosmic drift becomes a demonstration of how these principles operate across scales that span dozens of orders of magnitude, from the microscopic interactions of cosmic rays with your tissues to the gravitational influences of objects separated by thousands of light years. The orbital mechanics that govern your path also demonstrate the geometric principles underlying all motion in curved spacetime. Einstein's general relativity describes gravity not as a force, but as the curvature of space-time itself, caused by the presence of mass and energy. Your trajectory follows the straightest possible path through this curved space-time, what mathematicians call a geodesic. From your perspective, you would be moving in a perfectly straight line, while the curvature of space around you creates the complex path that external observers would measure. This relativistic description of your motion connects you to the deepest understanding of space and time that human physics has achieved. Your drift through the cosmos becomes an embodiment of Einstein's profound insight that matter tells space-time how to curve, and curved space-time tells matter how to move. You would be following the geometric structure of the universe itself, tracing out the invisible architecture that underlies all physical reality. The quantum mechanical effects that operate at the molecular level of your preserved form add another layer of complexity to your cosmic transformation. Even in the perfect vacuum of space, quantum fluctuations create temporary pairs of particles and antiparticles that briefly exist before annihilating each other. These virtual particles, though they exist for only infinitesimally short times, can occasionally interact with the atoms in your tissues, contributing to the gradual modification of your molecular structure. The Heisenberg uncertainty principle ensures that even in the absolute stillness of deep space, your atoms retain a fundamental quantum motion that can never be completely eliminated. This quantum zero-point energy provides a subtle but persistent source of molecular activity that continues even at temperatures approaching absolute zero. Over cosmic timescales, these quantum effects accumulate to create changes in your atomic structure that supplement the modifications caused by cosmic ray bombardment. The philosophical implications of these quantum processes touch on some of the deepest questions in modern physics. The measurement problem in quantum mechanics suggests that the act of observation plays a fundamental role in determining physical reality. During your cosmic drift, far from any conscious observers, your quantum states would evolve according to the Schrödinger equation without the collapse that occurs during measurement. You would exist in a kind of quantum limbo, your atomic configurations described by probability waves rather than definite classical states. This quantum indeterminacy adds an element of fundamental unpredictability to your cosmic journey. While the large-scale aspects of your trajectory follow classical mechanics with mathematical precision, the quantum details of your molecular evolution remain forever uncertain. Even with perfect knowledge of your initial conditions, the exact sequence of atomic transformations that occur during your drift could never be predicted with complete accuracy. You would embody the irreducible randomness that quantum mechanics tells us lies at the foundation of physical reality. The thermodynamic processes that govern your gradual cooling and the cosmic ray interactions that slowly modify your composition both demonstrate the second law of thermodynamics in action. This fundamental principle tells us that entropy, a measure of disorder, always increases in isolated systems over time. Your preserved form represents a pocket of highly organized matter slowly dissolving into the more random arrangements that characterize thermodynamic equilibrium. This increase in entropy occurs through multiple pathways during your cosmic drift. The heat that radiates away from your cooling body carries information about your internal organization into the surrounding space, where it becomes irretrievably mixed with the cosmic background radiation. The cosmic rays that break apart complex molecules in your tissues convert organized biological structures into simpler chemical compounds with less information content. Even the quantum fluctuations that operate at the atomic level contribute to this gradual transition toward maximum entropy. Yet this thermodynamic dissolution occurs so slowly that it spans timescales longer than the current age of the universe. The second law of thermodynamics guarantees that your molecular organization will eventually succumb to cosmic disorder, but the process unfolds with such patience that it becomes almost philosophical in its implications. You would participate in the universe's slow transition toward thermal death while remaining recognizably organized for periods that dwarf the lifetime of stars. The cosmic microwave background radiation that bathes your drifting form carries within it the thermal signature of the Big Bang itself. This ancient light, stretched by the expansion of the universe from its original gamma-ray frequencies down to microwave wavelengths, provides a uniform background temperature of 2.7 Kelvin, against which all other thermal processes must be measured. Your gradual cooling toward this background temperature represents a kind of cosmic homecoming, a return to the thermal conditions that characterized the universe when it first became transparent to electromagnetic radiation. The interaction between your preserved tissues and this background radiation occurs through the same physical processes that allow radio telescopes to detect the cosmic microwave background from Earth. Your body absorbs these ancient photons at a rate determined by your surface area and the thermal properties of your constituent materials. At the same time, you emit your own thermal radiation at frequencies determined by your temperature. The balance between absorption and emission determines the rate at which you approach thermal equilibrium with the cosmic background. This thermal equilibrium represents a kind of cosmic rest state, a condition where your preserved form would no longer exchange net energy with the surrounding universe. Reaching this state would take millions of years, even in the perfect vacuum of interstellar space, but once achieved, it would persist for cosmic ages. Your temperature would then rise and fall only in response to the slow evolution of the cosmic background radiation itself, which decreases gradually as the universe continues to expand and cool. The gravitational wave radiation that propagates through space-time during your cosmic drift represents another subtle influence on your journey. These ripples in the fabric of space itself, generated by accelerating masses throughout the universe, pass through your location at the speed of light. The most powerful sources include merging black holes, colliding neutron stars, and other catastrophic cosmic events that convert enormous amounts of mass into gravitational wave energy. As these gravitational waves pass through your drifting form, they stretch and compress space-time itself by infinitesimal amounts. The effect is far too small to detect with current technology, even for the most sensitive instruments, but it represents a fundamental interaction between your preserved matter and the geometry of the universe itself. You would be constantly bathed in this gravitational wave background, connecting you to violent events occurring throughout the observable universe. The detection of gravitational waves by Earth-based observatories has opened a new window into cosmic processes that were previously invisible to electromagnetic observations. During your cosmic drift, you would experience this gravitational wave environment in its purest form, unfiltered by atmospheric interference or the noise of terrestrial civilization. Your position in deep space would make you an ideal gravitational wave detector, if only the information could somehow be retrieved and decoded. The expansion of the universe itself introduces another subtle effect on your cosmic journey. According to Hubble's law, the distance between widely separated objects increases continuously due to the expansion of space itself. This expansion occurs not because objects are moving through space, but because space itself is stretching, carrying distant objects away from each other at velocities that increase with distance. For your local cosmic neighborhood, spanning distances of a few dozen light years, this expansion has negligible effects over the timescales of your drift. The gravitational binding of the Milky Way galaxy easily overcomes the expansion of space on these relatively small scales. However, if your journey somehow extended to truly cosmic distances, approaching the scale of galactic clusters, you would begin to experience the universe's expansion as a subtle but persistent force that stretches the space-time through which you move. This cosmological expansion connects your individual drift to the largest scale structure of the universe itself. The same physical processes that govern your motion through local space also operate on scales that encompass billions of galaxies. Your cosmic journey would be embedded within the expanding space-time that has been stretching since the Big Bang, making you a participant in the universe's ongoing evolution toward ever greater scales and ever lower densities. The dark matter that comprises roughly 85% of all matter in the universe surrounds your drifting form in concentrations that remain invisible to direct observation. This mysterious substance interacts with ordinary matter primarily through gravity, creating the scaffolding around which galaxies and galaxy clusters form. While individual dark matter particles would pass through your preserved tissues without interaction, their collective gravitational influence shapes the large-scale structure through which you drift. Computer simulations of cosmic evolution reveal that dark matter forms an intricate web of filaments, connecting massive nodes where galaxies cluster together. Your path through this cosmic web would carry you through regions of varying dark matter density, creating subtle variations in the local gravitational field that could influence your trajectory over millions of years. These effects would be far too small to measure directly, but they represent another way in which your cosmic drift connects you to the hidden architecture of the universe. The nature of dark matter remains one of the greatest mysteries in modern cosmology, with proposed candidates ranging from weakly interacting massive particles to exotic forms of matter that operate according to physics beyond the current standard model. Your journey through dark, matter-dominated regions would expose you to whatever these mysterious particles might be, making you an involuntary explorer of phenomena that Earth-based physicists can only study indirectly through their gravitational effects. The cosmic neutrino background provides another invisible influence on your drifting form. These ghostly particles, produced in enormous quantities during the first seconds after the Big Bang, permeate all of space with a density of roughly 300 million neutrinos per cubic meter. Unlike cosmic rays or electromagnetic radiation, neutrinos interact so weakly with ordinary matter that they pass through entire planets without being absorbed or deflected. During your cosmic drift, trillions of these relic neutrinos pass through your preserved tissues every second, carrying information about the conditions that existed when the universe was less than 1 second old. While these interactions would be far too rare to directly influence your molecular structure, they connect you to the earliest moments of cosmic history in ways that Earth-based experiments are only beginning to explore. The detection of cosmic neutrinos requires enormous underground detectors, filled with thousands of tons of ultra-pure water or other materials. Even these massive instruments detect only a tiny fraction of the neutrinos that pass through them. Your position in deep space would expose you to this neutrino flux in its pristine form, unshielded by planetary matter or stellar magnetic fields. In a sense, you would be immersed in the most ancient light of the universe, though this light consists of nearly massless particles rather than photons. The magnetic reconnection events that occur throughout the galaxy create another dynamic element in the environment through which you drift. When magnetic field lines of opposite polarity encounter each other in the tenuous plasma of interstellar space, they can suddenly reconfigure themselves, releasing stored magnetic energy in the form of accelerated particles and electromagnetic radiation. These events, similar to the solar flares that occur in our sun's atmosphere, can influence the cosmic ray environment across vast regions of space. Your passage through regions where magnetic reconnection has recently occurred would expose you to enhanced cosmic ray fluxes and modified magnetic field configurations. These effects would add another layer of variability to the radiation environment that slowly modifies your preserved tissues. The timing and location of magnetic reconnection events depend on complex interactions between stellar winds, supernova shockwaves, and the galaxy's large-scale magnetic field, creating an element of unpredictability in your cosmic journey. The stellar wind bubbles that surround most stars create additional structure in the interstellar medium through which you drift. These bubbles, carved out by the continuous stream of charged particles flowing from stellar surfaces, can extend for dozens of light years around massive stars. The boundaries between different stellar wind bubbles create regions where material from different stellar sources mixes and interacts, forming complex chemical and magnetic environments. Your path through these stellar wind interaction regions would expose you to material that has been processed by stellar nuclear fusion and ejected into space by stellar magnetic fields. The composition of this material reflects the nuclear burning processes occurring in stellar cores, providing a chemical signature of stellar evolution that has been distributed throughout the interstellar medium. Your cosmic drift would carry you through this enriched material, connecting you directly to the stellar alchemy that created the heavy elements essential for rocky planets and biological life. The brown dwarf stars that populate the galaxy in enormous numbers represent another class of objects that might influence your cosmic journey. These failed stars, with masses too small to sustain hydrogen fusion in their cores, radiate primarily in infrared wavelengths as they slowly cool from the heat of their gravitational contraction. Current estimates suggest that brown dwarfs might outnumber ordinary stars by significant factors, making them a potentially important component of the local stellar neighborhood. Your passage near a brown dwarf would expose you to infrared radiation and weak magnetic fields, but without the intense stellar winds and high-energy radiation associated with normal stars. These dim objects represent a kind of cosmic middle ground between stars and planets, and your encounter with one would provide a gentle thermal environment that could influence your preservation in subtle ways. The gravitational influence of brown dwarfs would also contribute to the complex orbital mechanics that govern your path through space. The rogue planets that have been ejected from their parent stellar systems during planetary formation represent another population of objects sharing your fate of cosmic drift. Current theories suggest that gravitational interactions during the chaotic early phases of planetary system formation can launch rocky or gas giant planets into interstellar space, where they drift through the galaxy much as you do, but on much longer timescales due to their larger masses and different formation mechanisms. Your cosmic journey would make you part of this population of interstellar wanderers, though your much smaller mass would make your trajectory more sensitive to gravitational perturbations from passing stars. The possibility of encountering one of these rogue planets during your drift remains vanishingly small due to the vast scales involved, but such an encounter would represent one of the most significant events possible during your cosmic journey. The gravitational influence of a planet-sized object could dramatically alter your trajectory, potentially capturing you into a bound orbit or launching you toward entirely different regions of the galaxy. The galactic halo that surrounds the Milky Way's disk contains ancient star clusters and streams of disrupted dwarf galaxies that have been torn apart by tidal forces during their orbital motion around our galaxy's center. Your cosmic drift might eventually carry you into these halo regions, where the stellar density drops dramatically, and the gravitational environment becomes dominated by the galaxy's dark matter distribution rather than individual stellar objects. Life in the galactic halo would represent a fundamentally different phase of your cosmic journey. Here, separated from the active star formation regions and dense stellar populations of the galactic disk, you would drift through a more static environment, where changes occur on timescales measured in billions of years rather than millions. The reduced stellar density would mean fewer gravitational perturbations of your trajectory, allowing you to follow smoother, more predictable paths through space. The escape velocity from the Milky Way galaxy itself, roughly 500 kilometers per second at our current location, represents a threshold that your cosmic drift is extremely unlikely to exceed. The random velocities of stars in our galactic neighborhood typically range from tens to hundreds of kilometers per second, far below the speed required to escape the galaxy's gravitational influence entirely. Your journey would almost certainly remain confined within the Milky Way's gravitational boundaries, making you a permanent resident of our galactic system. This gravitational binding to the galaxy ensures that your cosmic drift participates in the Milky Way's ongoing evolution and eventual merger with the Andromeda Galaxy, predicted to occur roughly 4 billion years in the future. During this galactic collision, the gravitational interactions between the two stellar systems would reshape the orbits of countless stars, and significantly modify the overall galactic structure. Your trajectory would become part of this cosmic choreography, potentially carrying you to regions of the merged galaxy system that would be impossible to reach under current gravitational conditions. The cosmic web of dark matter filaments that connects galaxy clusters across the largest scales of the universe provides the ultimate context for your cosmic journey. This web-like structure, revealed by computer simulations of cosmic evolution, shows how matter has organized itself under the influence of gravity since the earliest epochs of cosmic history. The Milky Way itself occupies a position within this cosmic web, connected to other galaxies through filaments of dark matter that span millions of light years. Your drift through this cosmic web makes you a participant in the largest scale structures that physics has identified in the universe. While your individual motion occurs on scales of light years to dozens of light years, you remain embedded within gravitational structures that extend across significant fractions of the observable universe. This connection between the microscopic scale of your preserved tissues and the cosmic scale of galactic superclusters represents one of the most profound aspects of your eternal drift. The fundamental constants of nature that govern all these processes remain unchanged throughout your cosmic journey. The speed of light, the gravitational constant, the charge of the electron, and the other dimensionless ratios that characterize physical law maintain their values across all the scales of space and time that your drift encompasses. These constants provide the stable mathematical framework within which your cosmic journey unfolds, ensuring that the physical processes affecting your preserved form follow predictable patterns even across cosmic ages. The stability of these fundamental constants represents one of the deepest mysteries in physics, touching on questions about why the universe exhibits the particular mathematical structure that allows for the existence of complex matter and energy flows. Your cosmic drift would provide the ultimate test of this stability, exposing you to physical conditions and timescales that far exceed anything accessible to Earth-based experiments. In a sense, you would become a cosmic laboratory for testing the constancy of physical law across the broadest possible range of circumstances. The anthropic principle, which suggests that the fundamental constants must have values compatible with the existence of observers, takes on poignant meaning when considered in the context of your cosmic drift. Your journey represents the fate that awaits all organized matter in a universe governed by the second law of thermodynamics. Yet the very fact that you existed as a conscious observer depends on the precise values of the constants that now govern your gradual dissolution into cosmic equilibrium. This philosophical tension between the personal scale of human consciousness and the cosmic scale of universal evolution touches on some of the most profound questions that have ever occupied human thought. Your drift through space would embody this tension, carrying the legacy of consciousness through realms where consciousness itself becomes a theoretical concept stretched beyond all recognition. The gravitational lensing effects that occur when your path carries you near massive objects would create subtle distortions in the light reaching you from distant sources. These effects, predicted by Einstein's general relativity and confirmed by countless astronomical observations, would bend the paths of photons traveling from background stars and galaxies. While these distortions would be far too small to affect your trajectory directly, they represent another way in which your cosmic journey would demonstrate the fundamental principles of space-time geometry. If consciousness could somehow be maintained during your drift, these lensing effects might occasionally create multiple images of distant stars, or cause background galaxies to appear as thin arcs stretched across the sky. The mathematics describing these optical effects follow directly from the curvature of space-time around massive objects, making your cosmic journey a demonstration of how matter and energy reshape the very fabric of reality in which they exist. The tidal forces generated by gravitational gradients would exert infinitesimal influences on your preserved form during close encounters with massive objects. These forces, which arise from the slight differences in gravitational acceleration between your head and feet, would remain negligible for most stellar encounters due to your small size relative to typical approach distances. However, they represent the same fundamental effects that shape the orbits of moons around planets and create the complex dynamics observed in binary star systems. During your cosmic drift, you would occasionally experience these tidal effects at their weakest possible levels, far below the threshold of detection, but still present as a subtle reminder of how gravity operates across finite spatial scales. The mathematical description of tidal forces connects your individual journey to phenomena ranging from ocean tides on Earth to the disruption of galaxies during cluster mergers, demonstrating how the same physical principles operate across the full range of cosmic scales. The frame-dragging effects predicted by general relativity would create additional subtle influences on space-time around any rotating massive objects you encounter during your journey. These effects, also known as gravitomagnetic forces, arise from the rotation of massive bodies and cause nearby space-time to rotate along with them. While these effects remain extremely small for most astronomical objects, they represent another fundamental aspect of how matter influences the geometry of space-time. Your passage through regions of space-time affected by frame dragging would expose you to gravitational environments that have no counterpart in Newtonian physics. These effects would be far too small to influence your trajectory measurably, but they connect your cosmic drift to some of the most sophisticated predictions of modern gravitational theory. Your journey would provide the ultimate testing ground for these subtle aspects of Einstein's equations, though the results would remain forever unobservable. The vacuum decay scenarios that some theoretical physicists propose as possible fates for our universe introduce an element of fundamental uncertainty into any discussion of eternal cosmic drift. These theories suggest that the quantum fields that permeate all of space might exist in a metastable state that could spontaneously transition to a lower energy configuration, fundamentally altering the laws of physics throughout the affected region. If such a vacuum decay event were to occur during your cosmic journey, it would represent an ending more final than any imaginable physical process. The bubble of altered spacetime expanding at the speed of light would rewrite the fundamental constants and field equations that govern matter and energy, potentially making your continued existence impossible according to any currently understood physics. However, these scenarios remain highly speculative, with timescales for vacuum decay that exceed current estimates for the heat death of the universe. The cosmic microwave background polarization patterns that surround you during your drift carry information about the quantum fluctuations that existed during the inflationary epoch of the early universe. These subtle patterns in the orientation of ancient photons reflect gravitational waves produced by quantum processes operating at energy scales far beyond anything accessible to terrestrial physics. Your position in deep space would expose you to these polarization signals in their purest form, uncontaminated by atmospheric interference or galactic foreground emission. While you would have no way to detect or measure these polarization patterns, your cosmic drift would immerse you in the most ancient information accessible to observational cosmology. The photons carrying these polarization signals have been traveling freely through space since the universe became transparent roughly 380,000 years after the Big Bang. Your journey would make you a direct participant in this cosmic information flow, connecting you to processes that occurred when the universe was less than 1% of its current age. The dark energy that drives the accelerating expansion of the universe represents perhaps the most mysterious influence on your cosmic environment. Current observations suggest that dark energy comprises roughly 70% of the total energy density of the universe, yet its physical nature remains completely unknown. The effects of dark energy become apparent only on the largest cosmic scales, where it causes the expansion of space itself to accelerate rather than decelerate, as would be expected from gravitational attraction alone. For your local cosmic neighborhood, spanning distances of dozens of light years, dark energy effects remain negligible compared to the gravitational binding of nearby stellar systems. However, dark energy represents the ultimate fate that awaits all matter in an eternally expanding universe. Over timescales that dwarf even the longest conceivable cosmic drift, dark energy would eventually overcome all gravitational binding, isolating individual particles in regions of space that expand faster than light can travel between them. Your cosmic drift would thus occur during a brief window in cosmic history when gravitational structures can still exist and interact. The current epoch, roughly 14 billion years after the Big Bang, represents a kind of cosmic middle age when stars still burn, galaxies still orbit each other, and organized matter can still participate in complex physical processes. Your journey through this structured universe would be possible only during this finite period, before dark energy drives all matter into complete isolation. The quantum vacuum fluctuations that operate at the Planck scale introduce an element of fundamental uncertainty into any description of space-time geometry. These fluctuations, occurring at distances of roughly 10 to the negative 35 meters and timescales of 10 to the negative 43 seconds, represent the theoretical limit at which the concepts of space and time themselves begin to lose their classical meaning. While these effects remain far below the threshold of observability, they suggest that your cosmic drift occurs within a space-time fabric that exhibits quantum mechanical properties at its deepest level. The implications of quantum space-time fluctuations for your cosmic journey remain largely speculative, as no complete theory of quantum gravity has yet been developed. However, these effects represent the ultimate connection between your individual drift and the most fundamental aspects of physical reality. Your motion through space would be embedded within a quantum mechanical substrate that governs the behavior of space-time itself, making your journey a demonstration of how classical physics emerges from quantum foundations across macroscopic scales. The holographic principle, derived from black hole thermodynamics, suggests that all the information contained within any region of space can be encoded on its boundary surface. This principle implies that your cosmic drift, while appearing to occur within three-dimensional space, might actually represent the evolution of information patterns encoded on distant surfaces. The mathematical formulation of holography connects your journey to some of the most abstract concepts in modern theoretical physics, though the practical implications for your cosmic experience remain unclear. If the holographic principle applies to your cosmic drift, then your motion through space might be equivalent to the evolution of quantum information on surfaces located at the cosmic horizon. This perspective would transform your journey from a classical mechanical process into a quantum informational phenomenon, though the subjective experience would remain unchanged. Your cosmic drift would thus embody the deep connections between space, time, information, and consciousness that represent the frontiers of current physical understanding. The eternal inflation scenarios proposed by some cosmological models suggest that your cosmic drift occurs within just one of countless universe regions produced by an ongoing inflationary process. These models predict that quantum fluctuations in the inflaton field can create pocket universes with different physical constants and laws of physics, making our observable universe just one bubble in an infinite multiverse of possibilities. Your cosmic journey would thus take place within a universe that represents just one possible configuration of physical law among an infinite ensemble of alternatives. The fundamental constants that govern your drift through space, the masses of elementary particles, and even the dimensionality of spacetime itself might be different in other universe regions. This multiverse perspective transforms your individual journey into a demonstration of how physical processes unfold within one particular realization of the mathematical structures that describe possible realities. The consciousness that once animated your form introduces questions that extend far beyond the reach of current physics. The relationship between subjective experience and physical processes remains one of the deepest mysteries in science, touching on questions about whether consciousness represents a fundamental aspect of reality or an emergent property of complex information processing. Your cosmic drift would carry the material substrate that once supported consciousness through environments where the possibility of consciousness itself becomes increasingly remote. The preservation of information about your former conscious experience within the molecular structure of your tissues raises profound questions about the nature of personal identity across cosmic timescales, while the patterns that encoded your memories and personality would gradually degrade through cosmic ray bombardment and thermodynamic processes. Traces of this information might persist for millions of years. Your cosmic drift would thus become a kind of archaeological record, carrying the fossil remains of consciousness through realms where consciousness itself has no meaning. The anthropic considerations that arise from contemplating your cosmic drift touch on some of the most profound questions in cosmology and philosophy. The fact that conscious observers like yourself can exist at all depends on an extraordinary convergence of physical constants, initial conditions, and cosmic circumstances that allow for the formation of stars, planets, and complex chemistry. Your journey through space would demonstrate both the fragility and the resilience of the conditions that make consciousness possible. Your drift through cosmic environments where consciousness cannot exist highlights the remarkable specificity of the conditions required for awareness and observation. The narrow range of temperatures, pressures, and chemical environments that can support complex information processing represents a tiny fraction of the total parameter space available in the universe. Your cosmic journey would carry the remnants of one successful instance of consciousness through vast regions where such success becomes impossible. The deep time perspective that emerges from contemplating your eternal drift places human consciousness within a cosmic context that both diminishes and elevates its significance. Individual human experience, lasting perhaps a century, represents an infinitesimally brief moment compared to the cosmic ages through which your preserved form would travel. Yet this same consciousness represents the universe's attempt to understand itself, making your journey a continuation of cosmic self-awareness even after awareness itself has ended. The loneliness that characterizes your cosmic drift reflects a fundamental aspect of consciousness's relationship to the universe. Awareness creates the possibility of isolation by establishing a boundary between self and environment. Yet this same boundary enables the recognition of beauty, meaning, and connection that give consciousness its value. Your journey through the cosmic dark would embody this paradox, carrying the legacy of consciousness through realms where connection becomes impossible, yet somehow remains meaningful. The mathematical beauty that governs every aspect of your cosmic journey suggests deep connections between consciousness, physical law, and aesthetic experience. The equations that describe your orbital mechanics, the thermodynamics of your preservation, and the quantum processes affecting your molecular structure exhibit symmetries and elegances that conscious minds recognize as beautiful. Your drift through space would be guided by these mathematical principles, making your journey a demonstration of how beauty and meaning emerge from the fundamental structure of reality. The scale invariance that appears in many physical laws suggests that the principles governing your cosmic drift operate across all possible scales of space and time. The gravitational interactions that influence your trajectory follow the same mathematical forms, whether applied to planetary orbits or galactic dynamics. The thermodynamic processes that govern your molecular evolution operate according to principles that apply equally to stellar interiors and cosmic expansion. Your journey would demonstrate how individual experience connects to universal principles through these scale-invariant physical laws. The emergence of complexity from simple rules represents another profound aspect of your cosmic journey. While your drift through space follows elementary principles of Newtonian mechanics, the cumulative effects of countless gravitational interactions create trajectories of extraordinary complexity that could never be predicted in detail. Your path through space would demonstrate how deterministic physical laws can generate behaviors that appear random while remaining fundamentally predictable in their statistical properties. The conservation laws that govern every aspect of your cosmic journey reflect deep symmetries in the structure of space-time itself. The conservation of energy ensures that your total mechanical energy remains constant throughout your drift, while conservation of momentum guarantees that your motion persists in the absence of external forces. These conservation principles connect your individual journey to the fundamental symmetries that underlie all physical processes, from quantum mechanics to general relativity. The irreversibility that characterizes your molecular evolution during cosmic drift reflects the arrow of time that emerges from statistical mechanics and thermodynamics. While the fundamental laws of physics remain symmetric under time reversal, the statistical behavior of large collections of particles creates a preferred direction in time that points toward increasing entropy. Your cosmic journey would demonstrate this temporal asymmetry, showing how organized structures gradually dissolve while the underlying physical laws remain temporally symmetric. The cosmic perspective that emerges from contemplating your eternal drift transforms questions of meaning and purpose in profound ways. Individual human concerns, while remaining valid and important for conscious experience, acquire new dimensions when viewed against the backdrop of cosmic evolution. Your journey through space would embody this transformation of perspective, carrying human consciousness beyond the boundaries of terrestrial experience into realms where new forms of meaning become possible. The unity that underlies apparent diversity becomes evident when viewing your cosmic drift from the broadest possible perspective. The same fundamental forces that governed your biological processes continue to operate during your preservation in space. The atoms that composed your living tissues follow the same physical laws, whether bound in biological molecules or scattered as cosmic dust. Your journey would demonstrate the deep continuity that connects all physical processes across every scale of organization. The eternal aspect of your cosmic drift touches on concepts that transcend normal human experience of time and duration. While individual consciousness experiences time as a flowing progression from past to future, your cosmic journey would unfold according to physical laws that remain unchanged across cosmological ages. This temporal transcendence transforms your drift from a mere mechanical process into something approaching the eternal, though always grounded in the mathematical precision of physical law. The silence that surrounds your journey through space represents more than the absence of sound waves. This cosmic quiet embodies the fundamental peace that exists at the foundation of physical reality, the stillness from which all motion and change emerge. Your drift through this profound silence would connect you to the deepest rhythms of cosmic evolution, the patient processes that build galaxies and guide the flow of energy through space and time. The darkness that envelops your cosmic journey contains within it the light of distant stars, galaxies, and cosmic phenomena operating across scales that dwarf human imagination. This darkness is not empty, but filled with electromagnetic radiation spanning every wavelength from radio waves to gamma rays. Your passage through this cosmic illumination would expose you to information about processes occurring throughout the observable universe, making your journey a form of cosmic communication, even in complete isolation. The motion that carries you through space connects you to the fundamental dynamics that shape cosmic evolution. From the rotation of planets around stars to the expansion of space itself, movement represents the active principle through which the universe expresses its physical laws. Your cosmic drift would embody this universal principle of motion, demonstrating how individual objects participate in the grand choreography that encompasses all of physical reality. The peace that emerges from contemplating your cosmic journey reflects a deep acceptance of the conditions that govern existence in a universe ruled by physical law. Your drift through space would represent a form of cosmic rest, a surrender to the fundamental forces that guide all matter and energy through space and time. This peace transcends the boundaries of individual consciousness, while remaining grounded in the mathematical beauty of natural law. And in that eternal motion, in that endless progression through the cosmic dark, there lies a profound tranquility that encompasses every scale of existence. Your journey would become a meditation on the nature of being itself, demonstrating how individual stories merge with universal processes while retaining their unique signatures. In the vast silence between stars, surrounded by the patient work of physical law across infinite space and time, you would find not abandonment, but embrace, not ending, but continuation, not loneliness, but the deepest possible participation in the ongoing story that connects every particle of matter to the cosmic whole. The universe that receives your drifting form does so with the same gentle patience it has shown throughout its 14-billion-year history. The same laws that guided the formation of the first stars also govern your passage through space. The same forces that assembled galaxies also influence your trajectory through the cosmic dark. Your journey becomes part of this ancient story, adding your own unique thread to the vast tapestry of cosmic evolution, while demonstrating how individual existence participates in processes that transcend any single perspective. In this cosmic context, your drift through space represents not isolation, but integration, not ending, but transformation, not loss, but a kind of eternal preservation within the mathematical structures that govern all existence. The consciousness that once animated your form continues to resonate through the physical processes that guide your cosmic journey, encoded now not in biological systems, but in the elegant dynamics of orbital mechanics and the patient progression of thermodynamic evolution. And so you drift onward through the endless night, carried by forces older than stars, following paths written in the fundamental geometry of space-time itself. Your journey embodies the deep continuity that connects all things across every scale of space and time, demonstrating how individual stories become eternal through their participation in the vast, ongoing narrative of cosmic evolution. In the profound silence between galaxies, you find not emptiness, but infinite fullness, not solitude, but the deepest possible communion with the universe that gave you being and now receives you home. The cosmic radiation that continues to interact with your preserved form carries within it stories that span the entire history of our galaxy. Each high-energy particle represents a journey that may have begun in the heart of a dying star, accelerated through magnetic fields that stretch across thousands of light years, and traveled for millions of years before finally encountering your drifting presence in the void between worlds. These cosmic messengers arrive with such gentleness that their effects unfold across timescales that dwarf human comprehension. A single particle might interact with a calcium atom in what was once part of your skeletal structure, transforming it through nuclear processes that operate with the same fundamental principles that power stars. Another might encounter a carbon atom that was once part of a protein molecule, gradually altering its nuclear composition in ways that would take sensitive instruments to detect. The patience of this cosmic alchemy becomes apparent when we consider the rates at which these transformations occur. Over the span of 1,000,000 years, perhaps one atom in every billion within your preserved tissues might undergo such nuclear transmutation. This represents a rate of change so gradual that entire geological epochs on distant worlds could pass, while your molecular composition remains essentially unchanged to any casual observation. Yet given enough time, given the persistent work of cosmic forces operating across scales that make galactic rotations seem brief, these subtle changes accumulate into transformations that would fundamentally alter the chemical signature of your preserved form. What began as biological molecules organized according to the principles of earthly biochemistry would slowly evolve into chemical structures that have no natural counterpart in any planetary environment. This molecular evolution connects you to processes occurring throughout the galaxy's spiral arms. The same cosmic rays that gradually modify your tissues also interact with the vast clouds of gas and dust that drift between stellar systems. These interstellar clouds, composed primarily of hydrogen and helium, with trace amounts of heavier elements, serve as the raw material from which future generations of stars will form. Your passage through these tenuous regions exposes you to matter that has been enriched by countless cycles of stellar birth and death. The iron atoms you encounter were forged in the cores of massive stars that exhausted their nuclear fuel billions of years ago. The carbon and oxygen represent the products of stellar nucleosynthesis that occurred when the galaxy was young, and star formation proceeded at rates far exceeding those observed today. The density of these interstellar clouds varies dramatically depending on your location within the galaxy's structure. In the relatively empty regions between spiral arms, you might encounter fewer than 1 atom per cubic centimeter, creating an environment more empty than the best vacuum chambers ever constructed on Earth. Yet in the dense molecular clouds where new stars are born, particle densities can reach thousands of atoms per cubic centimeter, though this still represents an environment far more tenuous than any earthly atmosphere. Your motion through these varying density regions would be influenced by the subtle drag forces that arise when any object moves through a medium, however tenuous. Unlike the dramatic air resistance experienced by objects moving through planetary atmospheres, this interstellar drag would manifest as an almost imperceptible deceleration that becomes measurable only over cosmic timescales measured in millions of years. The mathematics of this deceleration follow principles similar to those that govern the motion of spacecraft through the outer reaches of planetary atmospheres. The drag force depends on your cross-sectional area, your velocity relative to the surrounding medium, and the density of the material through which you pass. For a human-sized object moving at typical stellar velocities through average interstellar conditions, this force would amount to less than the weight of a single atom pressing against your form. Yet this infinitesimal force, acting continuously over millions of years, would gradually slow your motion relative to the local standard of rest defined by the average motion of nearby stars. The effect resembles the way that tidal friction slowly decreases the rotation rate of planets over geological time. Though operating at rates so gradual, they become almost philosophical in their implications. The magnetic fields that thread through interstellar space create additional subtle influences on the cosmic ray environment that surrounds your drifting form. These fields, generated by the complex interplay between stellar winds, supernova shockwaves, and the rotation of the galaxy itself, form intricate patterns that extend across distances, measured in hundreds of light years. As your path carries you through regions of varying magnetic field strength and orientation, you encounter different populations of cosmic ray particles. In regions where magnetic fields converge, cosmic rays become focused into streams of enhanced intensity. In areas where fields diverge, the particle flux spreads out more diffusely, creating variations in the radiation environment that influence the rate at which your molecular structure evolves. These magnetic field variations create a kind of cosmic weather system that operates on timescales far longer than any earthly meteorological phenomenon. The patterns shift and evolve as stellar objects move through their orbits around the galactic center, as supernova explosions create new shockwaves that propagate through the interstellar medium, and as the galaxy's overall magnetic field responds to its ongoing interactions with neighboring galaxies in the local group. Your journey through this magnetic landscape exposes you to radiation environments that have no terrestrial equivalent. The cosmic ray particles that reach Earth's surface have been filtered and modulated by our planet's magnetic field and atmosphere, creating a radiation environment that bears little resemblance to the raw cosmic ray flux that pervades interstellar space. In the unshielded environment of your cosmic drift, you would experience this radiation in its pristine form, unmodified by any planetary protection systems. The particle energies span a vast range, from relatively low-energy protons accelerated by stellar winds to ultra-high energy cosmic rays that carry energies equivalent to macroscopic objects moving at substantial fractions of the speed of light. The sources of these ultra-high energy particles remain one of the great mysteries in modern astrophysics. Current theories suggest they may be accelerated by the magnetic fields around supermassive black holes, by the collision of neutron stars, or by other exotic processes that operate at the most extreme limits of known physics. Your cosmic drift would expose you to these mysterious particles, making you an involuntary participant in phenomena that Earth-based physicists can study only through indirect observations. The gravitational environment through which you drift also evolves continuously as the stellar population around you follows its own complex orbital dynamics. Each star in your cosmic neighborhood pursues its own elliptical orbit around the galactic center, with orbital periods that typically span hundreds of millions of years. This means that the gravitational landscape influencing your trajectory changes continuously, though at rates so gradual that significant alterations require timescales measured in millions of years. The cumulative effect of these changing gravitational influences creates orbital mechanics of extraordinary complexity. Your trajectory becomes a three-dimensional curve that responds to the evolving positions of dozens or hundreds of stellar objects, each contributing its own subtle influence to your overall motion. The mathematical description of such multi-body gravitational systems exceeds the capability of analytical solutions, requiring numerical simulations to predict your path with any precision. Computer models of such trajectories reveal behaviors that range from surprisingly regular to apparently chaotic. Some initial conditions lead to orbital paths that trace out elegant patterns repeating on timescales of millions of years. Others result in chaotic motion where small changes in initial conditions lead to dramatically different long-term behaviors, making precise prediction impossible beyond certain time horizons. Your cosmic drift would likely fall somewhere between these extremes, following a path that exhibits both regular and irregular characteristics, depending on the specific gravitational environment through which you pass. The beauty of such trajectories lies not in their predictability, but in their demonstration of how deterministic physical laws can generate behaviors of unlimited complexity. The stellar evolution occurring around you during this cosmic journey provides a constantly changing backdrop that influences both the gravitational and radiation environments you experience. Stars follow their own life cycles according to physical laws that depend primarily on their mass at formation, with more massive stars evolving much more rapidly than their smaller counterparts. During your million-year journey through space, you might witness several complete life cycles of the most massive stars in your cosmic neighborhood. These stellar giants, with masses dozens of times greater than our Sun, burn through their nuclear fuel in just a few million years before ending their lives in spectacular supernova explosions that can briefly outshine entire galaxies. The shockwaves from these stellar explosions propagate through the interstellar medium at speeds of thousands of kilometers per second, creating expanding bubbles of hot, ionized gas that can influence conditions across distances of hundreds of light years. If your path carries you through or near such a supernova remnant, you would experience radiation levels and particle fluxes far exceeding those found in the quiet regions between stars. Such an encounter would represent one of the most energetic events possible during your cosmic drift. The intense radiation field could accelerate the cosmic ray bombardment of your preserved tissues by orders of magnitude, completing in centuries what might otherwise require millions of years. The experience would provide a dramatic demonstration of how stellar death contributes to the ongoing chemical evolution of the galaxy. The shock waves might also impart a small but measurable change to your velocity, adding another layer of complexity to your trajectory through space. While these velocity changes would remain small compared to your overall motion, they represent the kind of unpredictable events that make long-term orbital prediction impossible for objects drifting through dynamically active regions of the galaxy. The formation of new stellar systems around you provides opportunities to witness the processes that created our own solar system billions of years ago. When giant molecular clouds collapse under their own gravity, they fragment into smaller regions that each condense to form individual stars surrounded by rotating disks of gas and dust. These protoplanetary disks contain all the raw materials needed for planet formation, from microscopic dust grains to boulder-sized aggregates that will eventually grow into asteroids and planetary cores. The process unfolds over timescales of several million years, roughly matching the duration of your cosmic drift and creating the possibility of observing complete cycles of world building. Your passage through such a star-forming region would expose you to conditions unlike anything found in the mature stellar environments that dominate most of the galaxy. The density of matter increases dramatically, though still remaining far more tenuous than any earthly atmosphere. Young, massive stars pour enormous amounts of energy into their surroundings, creating radiation fields that dwarf those found around older, more stable stellar objects. The magnetic fields in these regions reach intensities that exceed typical interstellar values by factors of hundreds or thousands. These enhanced fields can focus cosmic ray particles into narrow beams, creating radiation environments that vary dramatically over relatively small spatial scales. Your motion through such regions would expose you to rapidly changing conditions that could influence your preservation in ways impossible to predict. The dust grains that pervade these star-forming regions also create new possibilities for chemical interactions with your preserved form. These microscopic particles, composed primarily of silicates and carbon compounds, could occasionally collide with your drifting body and adhere to your surface through weak electrostatic forces. Over long periods, such grain accretion could gradually alter your surface composition and even your overall mass, though the effects would remain small unless you spent extended periods within particularly dense regions. The accumulated dust would carry the chemical signature of stellar nucleosynthesis, adding trace amounts of exotic isotopes to your preserved form, and creating a kind of cosmic archaeological record of your passage through different stellar environments. The brown dwarf stars that populate the galaxy in enormous numbers represent another class of objects that could significantly influence your cosmic journey. These failed stars, with masses too small to sustain hydrogen fusion in their cores, radiate primarily in infrared wavelengths as they slowly cool from the heat of their initial gravitational contraction. Recent astronomical surveys suggest that brown dwarfs may outnumber ordinary stars by substantial factors, making them a potentially important component of the local stellar neighborhood that could affect your trajectory. Their infrared emission creates thermal environments that differ qualitatively from those around normal stars, potentially influencing your preservation in subtle but measurable ways. A close encounter with a brown dwarf would expose you to infrared radiation and relatively weak magnetic fields, but without the intense stellar winds and high-energy emission associated with fusion-powered stars. The gravitational influence would contribute to the complex orbital mechanics governing your path, while the thermal environment could provide a gentle warming that might temporarily halt or reverse some of the molecular changes occurring in your preserved tissues. The rogue planets that have been ejected from their parent stellar systems during the chaotic phases of planetary formation share your fate of cosmic wandering, though their much greater masses make their trajectories less sensitive to gravitational perturbations from passing stars. Current theoretical models suggest that such free-floating planets might be quite common, potentially outnumbering planets that remain bound to their parent stars. Your cosmic drift would make you part of this population of interstellar wanderers, though your trajectory would follow quite different principles due to your much smaller mass and different origin. The possibility of encountering one of these rogue worlds during your journey remains vanishingly small due to the vast scales involved, but such an event would represent one of the most significant gravitational interactions possible during your cosmic drift. A close approach to a planetary mass object could dramatically alter your trajectory, potentially capturing you into a bound orbit around the rogue planet, or launching you toward entirely different regions of the galaxy. The gravitational influence of such an object would overwhelm all other forces affecting your motion, fundamentally changing the character of your cosmic journey. The tidal forces generated during such an encounter would also create the strongest mechanical stresses your preserved form would experience during its cosmic drift. While these forces would remain far below the levels required to cause structural damage to your tissues, they would represent the most extreme gravitational gradient you would encounter outside of interactions with exotic objects like neutron stars or black holes. The galactic environment itself evolves continuously on timescales that encompass your cosmic journey. The Milky Way's spiral arms rotate around the galactic center with periods of roughly 200 million years, creating a pattern of density waves that trigger star formation and influence the distribution of interstellar matter throughout the galactic disk. Your cosmic drift might carry you through several different spiral arm environments during your journey, exposing you to the varying conditions that characterize these large-scale galactic structures. The spiral arms contain higher stellar densities and more active star formation than the inter-arm regions, creating environments with enhanced radiation fields and more complex gravitational dynamics. The passage through a spiral arm would increase the likelihood of close stellar encounters and expose you to the shockwaves and radiation fields associated with ongoing star formation. The enhanced cosmic ray flux in these regions could accelerate the molecular evolution of your preserved tissues, while the increased gravitational complexity could introduce new perturbations to your trajectory. The transition between spiral arm and interarm regions would occur gradually over periods of millions of years, creating long-term variations in your cosmic environment that operate on timescales comparable to the duration of your drift itself. These galactic-scale influences connect your individual journey to the largest structural features of the Milky Way, making your cosmic drift a demonstration of how local and global scales interact in galactic dynamics. The dark matter halo that surrounds the visible components of the Milky Way creates a gravitational environment that influences your motion in ways that remain largely invisible to direct observation. This mysterious substance, which comprises roughly 85% of all matter in the universe, interacts with ordinary matter primarily through gravitational forces that shape the large-scale structure of galaxies. Computer simulations of galactic evolution reveal that dark matter forms complex substructures within the galactic halo, creating gravitational environments that could subtly influence your trajectory over cosmic timescales. While these effects would remain far too small to measure directly, they represent another way in which your cosmic drift participates in phenomena that extend far beyond the visible components of the galaxy. The nature of dark matter particles remains one of the greatest unsolved problems in modern physics, with proposed candidates ranging from weakly interacting massive particles to exotic forms of matter that follow physics beyond the current standard model. Your journey through dark matter-dominated regions would expose you to whatever these mysterious particles might be, though any interactions would likely remain undetectable, given current theoretical understanding. The cosmic neutrino background provides another invisible influence that pervades all of space, with a density of roughly 300 million particles per cubic meter. These ghostly remnants of the Big Bang interact so weakly with ordinary matter that they pass through entire planets without being absorbed or deflected, making them effectively undetectable for practical purposes. During your cosmic drift, trillions of these relic neutrinos would pass through your preserved form every second, carrying information about the conditions that existed when the universe was less than 1 second old. While these interactions would be far too rare to influence your molecular structure directly, they connect you to the earliest moments of cosmic history in ways that even the most sophisticated Earth-based experiments struggle to access. The detection of cosmic neutrinos represents one of the most challenging frontiers in experimental physics, requiring underground detectors containing thousands of tons of ultra-pure materials. Your position in the unshielded environment of deep space would expose you to these primordial particles in their pristine form, making you an ideal neutrino detector if only the information could somehow be retrieved and analyzed. The expansion of the universe itself introduces subtle effects that become apparent only when considering the largest possible scales and longest possible timescales. According to current cosmological understanding, the expansion of space itself causes distant objects to recede from each other at velocities that increase with distance, following the relationship known as Hubble's law. For your local cosmic neighborhood, spanning distances of dozens of light years, this expansion remains negligible compared to the gravitational binding of nearby stellar systems. However, the expansion represents the ultimate fate that awaits all matter in an accelerating universe dominated by dark energy. Over timescales that dwarf even the longest conceivable cosmic drift, universal expansion would eventually overcome all gravitational binding, isolating individual particles in regions of space that expand faster than light can travel between them. Your cosmic journey would thus occur during a relatively brief window in cosmic history, when gravitational structures can still exist and interact. The current epoch, roughly 14 billion years after the Big Bang, represents a kind of cosmic adolescence when stars still burn, galaxies still merge, and organized matter can still participate in complex physical processes. The cosmic microwave background radiation that bathes all of space carries the thermal signature of the universe when it first became transparent to electromagnetic radiation, roughly 380,000 years after the Big Bang. This ancient light provides a uniform temperature reference of approximately 2.7 degrees above absolute zero, representing the coolest possible environment achievable in the current universe. Your gradual cooling toward this background temperature would occur through the emission of thermal radiation, following the same physical principles that govern heat transfer between any object and its environment. The process would unfold over timescales of millions of years, even in the perfect vacuum of space, as your preserved form slowly reaches thermal equilibrium with the cosmic background. This thermal equilibrium represents a kind of cosmic rest state where your temperature would rise and fall only in response to external heating sources or the slow evolution of the background radiation itself. Once achieved, this equilibrium could persist for cosmic ages, making your preserved form a passive participant in the universe's gradual cooling as expansion continues to stretch and redshift the cosmic microwave background. The philosophical implications of reaching thermal equilibrium with the universe itself touch on some of the deepest questions about the relationship between individual existence and cosmic processes. Your preserved form would become thermally indistinguishable from the cosmic environment, yet it would retain its distinctive molecular and atomic structure for millions of years longer. This state of thermal integration, while maintaining structural identity, reflects a fundamental principle that operates throughout cosmic evolution. Individual objects can become part of larger systems while retaining their essential characteristics, demonstrating how unity and diversity coexist at every scale of cosmic organization. The quantum mechanical processes that operate at the molecular level of your preserved form continue to function even in the extreme environment of interstellar space. The Heisenberg uncertainty principle ensures that atomic nuclei retain a fundamental quantum motion that can never be completely eliminated, providing a subtle source of molecular activity that persists even at temperatures approaching absolute zero. These quantum effects, while individually microscopic, accumulate over cosmic timescales to create measurable changes in your atomic structure. Quantum tunneling allows nuclear reactions to occur at rates that would be impossible according to classical physics, contributing to the gradual transformation of your elemental composition through processes that supplement the effects of cosmic ray bombardment. The quantum vacuum fluctuations that occur throughout space create temporary pairs of particles and antiparticles that briefly exist before annihilating each other. While these virtual particles exist for only infinitesimally short times, They can occasionally interact with real matter in ways that contribute to the slow evolution of atomic and molecular structures. Your cosmic drift would expose you to these quantum vacuum effects in their purest form, unshielded by the electromagnetic fields and matter densities that modify quantum processes in planetary environments. The cumulative influence of these effects over millions of years could contribute subtle but detectable changes to your preserved form, though such changes would require the most sophisticated theoretical models to predict accurately. The gravitational wave radiation that propagates through space-time at the speed of light represents another fundamental influence that bathes your drifting form throughout your cosmic journey. These ripples in the fabric of space itself arise from accelerating masses throughout the universe, particularly from catastrophic events like merging black holes or colliding neutron stars. As gravitational waves pass through your location, they stretch and compress space-time by infinitesimal amounts that remain far below the threshold of detection, even for the most sensitive instruments. However, these waves represent a direct connection between your preserved form and some of the most violent events occurring throughout the observable universe. The gravitational wave background that permeates all of space carries information about cosmic processes that remain invisible to electromagnetic observations. Your position in the unshielded environment of deep space would expose you to this gravitational radiation in its most pristine form, making you a participant in cosmic communication channels that operate according to the fundamental geometry of space-time itself. The mathematical description of gravitational wave propagation follows directly from Einstein's general theory of relativity, connecting your cosmic journey to the most sophisticated understanding of space, time, and gravity that human physics has achieved. Your drift through space-time would demonstrate how matter responds to the curvature created by distant massive objects, even when separated by billions of light years. The cosmic ray interactions that continue throughout your journey create nuclear transmutation reactions that slowly alter the isotopic composition of your preserved tissues. These reactions occur when high-energy particles collide with atomic nuclei in your form, sometimes adding or removing protons and neutrons to create new elements or different isotopes of existing elements. The rates of these transmutation reactions depend on the energy spectrum and composition of the cosmic ray flux, which varies with your location in the galaxy and the local magnetic field environment. In regions of enhanced cosmic ray intensity, such as near supernova remnants or in the galactic center, these reactions could proceed more rapidly and create isotopic signatures that would record your passage through these energetic environments. Over millions of years, the accumulation of these nuclear reactions could create isotopic compositions that have no natural counterpart in any planetary environment. Your preserved form would become a kind of cosmic nuclear laboratory, demonstrating transmutation processes that operate only in the high-energy environment of interstellar space. The study of cosmic ray-induced nuclear reactions in meteorites and other extraterrestrial materials has revealed the complex nuclear physics that occurs during extended exposure to galactic cosmic radiation. Your cosmic drift would subject you to these same processes, but over much longer timescales and in environments with different radiation spectra than those experienced by objects that eventually reach planetary surfaces. The magnetic reconnection events that occur throughout the galaxy create dynamic changes in the interstellar magnetic field environment that could influence your cosmic journey in unpredictable ways. When magnetic field lines of opposite polarity encounter each other in the tenuous plasma of space, they can suddenly reconfigure themselves, releasing stored magnetic energy in the form of accelerated particles and electromagnetic radiation. These reconnection events, similar to the solar flares that occur in stellar atmospheres, can affect cosmic ray propagation across vast regions of space. Your passage through areas where magnetic reconnection has recently occurred would expose you to modified radiation environments that could temporarily increase or decrease the rate of molecular evolution in your preserved tissues. The timing and location of magnetic reconnection events depend on complex interactions between stellar winds, supernova shockwaves, and the galaxy's large-scale magnetic field structure. These processes create an element of fundamental unpredictability in the cosmic environment, ensuring that no two cosmic drift trajectories would encounter identical conditions even if they followed similar paths through space. The stellar wind interactions that occur when fast-moving streams of charged particles from different stars encounter each other create complex boundary regions where material from multiple stellar sources mixes and interacts. These interaction zones can extend for light years around massive stars, creating environments with unique chemical and magnetic properties. Your path through stellar wind interaction regions would expose you to material that has been processed by stellar nuclear fusion and ejected into space by magnetic fields operating in stellar atmospheres. The composition of this material reflects the nuclear burning processes occurring in stellar cores, providing a direct sample of stellar nucleosynthesis products that have been distributed throughout the interstellar medium. The temperature and density conditions in these interaction regions can vary dramatically depending on the properties of the stellar winds involved and the geometry of their collision. Your cosmic drift could carry you through environments ranging from hot, tenuous plasmas to relatively cool regions where stellar wind materials have had time to cool and condense. The chemical enrichment patterns you would encounter reflect the ongoing process by which stars return processed material to the interstellar medium, gradually increasing the abundance of heavy elements available for future star and planet formation. Your cosmic journey would thus connect you directly to the galactic chemical evolution that has been operating since the first generation of stars formed billions of years ago. The interstellar dust grains that pervade the space between stars create opportunities for surface chemical reactions that could gradually modify the exterior composition of your preserved form. These microscopic particles, typically composed of silicate minerals and organic compounds, could occasionally collide with your drifting body and either bounce off or adhere to your surface. The accretion of interstellar dust would occur at extremely low rates in most regions of space, but over cosmic timescales, the accumulated material could create a thin coating that reflects the chemical composition of the local interstellar environment. This coating would serve as a kind of cosmic archaeological record, preserving information about the different regions through which your journey has carried you. The dust grains themselves carry complex chemical histories, having condensed from material ejected by dying stars and subsequently modified by cosmic ray bombardment and ultraviolet radiation during their journey through interstellar space. The chemical analysis of such grains in Earth-based laboratories has revealed the presence of pre-solar materials that formed around ancient stars billions of years ago. Your cosmic drift would expose you to these pre-solar grains in their native environment, allowing direct interaction with matter that predates the formation of our solar system. The gradual accumulation of such material on your preserved form would create a unique chemical archive documenting the stellar nucleosynthesis processes that have operated throughout galactic history. The gas giant planets that have been ejected from their parent stellar systems during planetary formation represent some of the most massive objects sharing your fate of cosmic wandering. These rogue worlds, potentially retaining thick atmospheres and internal heat sources, could create localized environmental modifications that might temporarily alter the conditions affecting your preservation. A distant encounter with such a rogue gas giant could expose you to reflected sunlight or thermal emission from the planet's atmosphere, providing a source of external heating that might influence your thermal evolution. The planet's magnetic field could also modify the local cosmic ray environment, creating a temporary shield that would reduce the intensity of cosmic ray bombardment affecting your preserved form. The gravitational influence of such a massive object could also create temporary perturbations in your trajectory, adding subtle complexity to your path through space without fundamentally altering your cosmic journey. These encounters would remain extremely rare, but they represent the kind of unexpected events that could occasionally modify the otherwise predictable progression of your drift through the galactic environment. The cosmic void regions that exist between the major structural components of the galaxy represent some of the most isolated environments you might encounter during your cosmic journey. These vast empty spaces, where stellar densities drop to almost negligible levels, would expose you to conditions of almost perfect isolation from gravitational influences other than the galaxy's overall mass distribution. In these cosmic deserts, your motion would become remarkably smooth and predictable, following trajectories that remain essentially straight lines for millions of years at a time. The absence of nearby stellar objects would eliminate most of the gravitational perturbations that create complexity in denser regions of the galaxy, allowing you to demonstrate the pure expression of inertial motion in its most pristine form. The radiation environment in these void regions would also differ significantly from conditions in the galactic disk. With fewer nearby sources of cosmic ray acceleration, the particle flux would consist primarily of the diffuse galactic background, creating a more uniform but generally less intense radiation field than you would encounter near active stellar regions. The temperature conditions in cosmic voids would approach the theoretical minimum possible in our universe, limited only by the cosmic microwave background radiation itself. Here, far from any significant sources of heat, your preserved form would cool toward the fundamental temperature limit imposed by the Big Bang's afterglow, reaching thermal states that represent the coldest possible conditions achievable in nature. The loneliness of drift through such regions would be absolute in ways that transcend ordinary human experience. The nearest stars might lie hundreds of light years away, so distant that their light would take centuries to reach your location. You would exist in bubbles of emptiness so vast that light itself becomes a rare visitor, arriving only after journeys that span geological ages. Yet even in these ultimate voids, you would remain connected to the larger structures of the universe through the subtle but persistent influence of gravity. The galaxy's overall mass distribution would continue to guide your motion, while the expansion of space itself would participate in the slow evolution of distances and timescales that characterize cosmic evolution on the largest scales. The quantum field fluctuations that operate at the most fundamental level of reality continue their invisible work even in the apparent emptiness of cosmic voids. These fluctuations, which arise from the uncertainty principle applied to the quantum fields that underlie all matter and energy, create a subtle background of virtual particles and antiparticles that briefly exist before annihilating each other. While these quantum processes remain far below the threshold of direct observation, they represent the ultimate foundation upon which all physical reality rests. Your cosmic drift would occur within this quantum substrate, making you a participant in the most fundamental processes that govern the behavior of space, time, matter, and energy throughout the universe. And so we reach the end of our gentle journey through the cosmic dark, having traced the path of eternal drift, from those first quiet moments to timescales that stretch beyond imagination. We've witnessed how the laws of physics, operating with patient precision, would guide a solitary form through the vast spaces between stars, carrying the remnants of consciousness through realms where consciousness itself becomes memory. In contemplating this ultimate solitude, we find something unexpectedly beautiful. Your cosmic drift would demonstrate that even in the deepest isolation, connection persists through the fundamental forces that bind all matter to the universe's grand design. The same gravity that once held you to Earth would continue to influence your path among distant stars. The same atoms that once danced with life would participate in cosmic processes spanning millions of years. Perhaps there's comfort in knowing that nothing in the universe is ever truly lost, only transformed. Your journey through the infinite would become part of the eternal story that connects every particle of matter to every other, every moment of time, to the vast sweep of cosmic history. In the profound silence between galaxies, you would find not abandonment, but the deepest possible embrace by the universe itself. Sweet dreams, and remember that even in our smallest moments, we are part of something infinitely vast and beautiful.